I just want to introduce our speaker for our Git Tech Talk today. This is Randall Schwartz. Most of you will recognize him from his many published books on Perl, such as Learning Perl. He's also a founding member of the Perl Mongers Group, the founder and president of Stonehenge Consulting, a widely recognized open source trainer and advocate, and a contributor to Git. So thank you very much, Randall Schwartz, for coming today. And this is the Git Tech Talk.
Thank you, Larry. Thank you. Thank you, everyone. Thank you for the honor of allowing me to speak to you today. I also want to thank my friend Linus Torvalds for kind of leaving you hanging about 6 months ago about what Git really was all about. Left a great opportunity for me to come down and actually do my talk that I'd written about a year ago to do roughly the same thing, fill in all the gaps. He told you what Git wasn't about 6 months ago. I'm telling you what Git is, so it'll be more direct for the people that are looking at Git as a chance of participating. I think my talk's going to run about 45 minutes or so there'll be some time at the end for questions. So feel free to interact with me a little bit when we get down to the end. So I have to begin, of course, by giving my laptop a whack until it gets running here. Hello, hello. There we go. I do want to give a bit of a disclaimer. I have actually been around the Git project since it first began. Rather fortunate coincidence was that Linus moved to Portland, Oregon, my home, about the time that he started Git. And I invited him out for a chance to sample some of the local microbrew. And he took me up on that. And I said, so what are you doing these days? And he goes, well, BitKeeper just went away, and we have to have something to work the Linux kernel with. So I've been working on this little thing called Git. And so I had a great conversation with him right at the very beginning of when it all started. So I've been around since the beginning of it. And I have personally used Git on small projects. And I've used, of course, other systems in my 25-year career, almost 30-year career now, getting old, on both small and large projects. So I have a pretty good sense of what change control management's all about and things like that. And I've also read a lot of people talk about Git, seen a lot of things on the mailing list. So I've been tracking Git since the beginning that way. And I've even provided some patches for Git and suggestions for user interface changes. And I have worked on small teams with Git, just small being in the order of 3 or 4 people, nothing really large yet. And so I just also want to say that I don't have any experience working in a large team with Git. So if that makes me less credulous, well, ignore that, OK? So let's answer the question that Linus sort of stepped around a little bit when he gave his talk 6 months ago. So Git is a change control manager. It's managing changes to a tree of files over time. And the keyword tree there is important. It's not an individual file change control management system like, say, RCS or even CVS. So Git is optimized in a particular set of ways that Linus found useful for the Linux kernel team. For example, it's optimized for distributed development because the Linux kernel is being developed in many, many different countries simultaneously. We have to have some way of having everybody have their own copy of things to be able to edit it and so on. And because there's about 35,000 files in the Linux kernel, it has to work really fast. It has to work really well with large file sets, with lots and lots of files. You can't have something that is proportional to the number of things in a change set. It's also really optimized for complex merges. This means that we can take 2 people's work and bring them together easier probably with Git than almost anything else out there. I would say anything else, but somebody would challenge me on that, I'm sure. It's also optimized in an interesting way for really, really, really encouraging you to be speculative. We'll see how this works in a few minutes, but to really just sort of say, I'm going to try something here. And I don't know about you, but when I try things, sometimes they don't work. And I don't want other people to know that I tried something that didn't work. And so this has kept me in the past from, say, making the changes and keeping track of them in the centralized repository because I don't want people to see that I made mistakes. So I'm kind of embarrassed that way when that happens. What's great about Git is I can make all these changes and all these managed changes in my local repo and never publish it if it never works out. There's not even an advancement of a version number to even notice that something went wrong. So it's really good. It really encourages this sort of speculation, which is very good. It's also optimized at being fast. So just getting things done really, really quickly, like a half a second for a merge or a couple seconds to do a diff and things like that for 35,000 files in the Linux kernel tree. It's also optimized for just working, to just continue to work. There's very few ways that things could possibly blow up, and most of them won't result in the loss of any data. So your stuff isn't going to get lost. It's very, very careful to check things as they're being created and to only add objects in the tree and so on. So to contrast that with what Git is not optimized for, let's, because Git's not everything. It's optimized for these sets of things. It's not optimized for tracking permissions and ownership. Because as was decided by the design of the thing, it's really about source code management. Source code doesn't have permissions and ownership. Source code only becomes things that have permissions and ownership when they're finally installed. So it's up to your install tools, your build tools, to actually add that layer of metadata to it. And it's also not optimized for tracking individual files with a separate history. So for example, one task that Git will definitely never be really good at would be, say, putting your entire home directory under Git. Because the relationship of changing some file in your home directory compared to some other file in your home directory generally doesn't have a relationship. But Git really wants to make sense out of the fact that you made both of these changes, and it's not good for that sort of stuff. Putting /etc under Git would also be a bad idea too, although people have tried it. People are trying some really weird stuff with Git now. It's also not optimized for making things painful. Okay, we got rid of that. We said that's not really anything we want to make Git do. So why? Again, some of the background here, it was absolutely essential for Linux kernel development because it was created about 2 years ago, 2.5 years ago, when BitKeeper suddenly became unavailable. And the story behind that, you can go read on the net. I won't bring up the bad karma from that. But what's great is that with Git, you don't have to be special to start making changes that can be tracked. You can simply take the repo for the entire Linux kernel or the KDE tools or Wine or whatever these projects are that are using Git. You just take the entire repo and you just start making commits in your own workspace. And then you can publish that. And if people want to accept that back in, that's fine, but they can do it at their leisure. You don't have to sort of first go, please make me one of the SVN committers here or one of the CVS committers here. You just go ahead and start making your changes and you publish it when you're ready. So anyone, like I said, can clone the tree. They can make and test their local changes, just make sure everything works before publishing it out to the center. And then Git has 2 modes for publishing your changes. You can either send them back in as patches via email in a sort of highly structured email that's human readable but has all enough right bits in there so you can tell what change this is against, what change set this is against, and so on, and even what file it is. But of course, you can also publish your own repository. So if you have a publicly available web server or a machine that you can have inbound connections to, you can put a Git server up and say, okay, I've made these fixes to the software you're developing. They're published at this address. Here's the URL. Come look at them, and if you want them, merge them into the mainstream, because that would be really handy. So it's great. You can either submit them as patches or publish them as a repo. And what's great also is that the tools that allow me to develop individually, of course, the rest of the world will still continue to develop more on the same software, so there are good tools for tracking that and being able to make my changes now relate to this release instead of the previous release. So I can rebase my changes. We'll see how those tools work in a few minutes. So really, although kernel.org is still the place where you would get your Linux kernel from, it's really just a convenient watering hole. It could just be that we all connect to Linus's laptop wherever he happens to be, and it would work exactly the same way. Or any one of the 10 lieutenants that are sort of looking over each individual area, they all have exactly the same code. So we can connect anywhere, really, and pick up the code and the changes that we want to get. They all have the same history. So how does it do that? Well, it has a couple of specific properties that make it really interesting. One is the notion of a universal public identifier. You will see in a few moments this notion of the SHA-1. We have a 40-character hex string that is absolutely unique, universally unique identifier, and it allows us to talk consistently, no matter where we are, about a particular commit or a particular file or a particular directory with direct ease and in a way that's cryptographically secure. None of this, my 245 release is really your 992 release, and we have to somehow coordinate the numbers to make it make sense once we come together. Another key feature of Git is that it understands multiple protocols. So in other words, we can actually access a Git archive over HTTP, relatively dumb protocol there. If we're going to be doing uploading, pushing back, we're probably going to be using something like SSH. So we SSH, and there's a restricted shell available, so we can have controlled uploads through SSH. And there's also the Git protocol, which is a good way to pull things down because my Git client, when it's talking to a Git server, can compare notes about what it needs to pull down and do the transaction much more efficiently. Another thing that's really interesting about the way Git has as a property is that the objects, the files, the directories, the commits, the tags, are all stored in a very efficient manner. We'll see how that works in a few minutes as well. Another thing that's essential to Git that makes it work really well is that everyone has the entire repo. And the disk is cheap. Not only that, but because of the efficiency and the way Git stores it, you can take the entire history of the 2.6 Linux kernel in the Git repo, and it is 1/2 the size of the current checkout. So you've got this entire history, thousands and thousands of changes, all available to you, and it's only and it's still only 1/2 the size of just checking out the latest version. So it's actually faster to download a Git repo of the Linux kernel than it is to download the current checkout. That's the kind of compression that's achievable here. I think the X11 people, X11R6, when they did that, they found that every change, X11R6 all the way back to the beginning, made the repo only twice as big as the current checkout. So again, very efficient way to store history. We'll take questions at the end. Thanks. Okay. Easy branching and merging. Like I said, it's very, very easy to start off and try something new and creating your own branch and then bringing that back together and figuring out where things are. It's very, very easy to do that. Also, because of the way that Git is tracking all the commits, all the changes to your system, computing the common ancestor, a big problem when you're dealing with CVS, for example, is immediately computable. You always know all the way back to where the common ancestors came for a particular commit and a particular merge. And the nice thing is that patches and repo updates can be transported or mailed, so that means that we don't have to have a live connection. We can send it over, SMTP from hop to hop until it gets to the destination. Binary patches are also supported. That means I can use a Git archive to track everything on my website, for example, all my JPEGs, images, things like that are related to building my particular site. So it's pretty cool. Now, the universal identifier, as I mentioned a moment ago, SHA-1, it's a king. Every object has a unique SHA-1 to identify it. And object, in this sense, is everything that's in the object repository, which consists of the contents of a file. So obviously, we want to track the contents. That's the whole point of a source code management software, is to track the contents. So we call those blobs in the terminology of the Git software. A tree, so a directory of blobs or other trees recursively. So given a SHA-1, I can drill down through my object tree in my repository and come up with the entire tree from there down. So the SHA-1 points at a tree object, which points at other tree objects and points at the blobs. And each one of those points at more tree objects, more blobs, and so on all the way down. The nice thing about the way this is done and the way it's been laid out is if you move an entire subtree from one place to another in your working view, it still will have the same SHA-1 for the top of the tree. So we don't have to store 2 different copies of that in the repository because the SHA-1 remained the same because everything below it was still the same. So this really allows for efficient renaming, reorganizing without having to get a 2nd and 3rd and 10th copy of that same JPEG or the same set of files in this particular subdirectory. It's really it's a nice feature of that. Another thing that ends up in the object tree are commits. A commit is really the ultimate product of making changes to the software. So a commit consists of a tree SHA-1. So this uniquely identifies all of the stuff down below it, as we just said on the tree thing there, plus 0 more parent commits. Typically a commit making changes is going to be changes to something that already had changes made to it. Most of the time it'll be linear, so lots of commits that have 1 parent, but there'll be some commits that have 2 or more parents if it was a merge, for example. So this gives us, again, a complete tree backwards. Now, the interesting thing about this is that means if I know a particular SHA-1, I not only have the entire tree that it represents, so I know precisely all the files that belong to it and all the directories that those files are contained in, but I also know the commit going back in time, or multiple commits if it was a merge. This means that a given SHA-1 identifies not only what's currently there, but also the entire history, and it's cryptographically strong. So now we have an entire signed history of the 2.6 kernel by knowing 1 single number. and using the object trees to translate that back into both the snapshots over time and the commits that led us there and all the reasons for that. A commit will also have a message about why the commit was actually made, the little standard text that you would have in a commit message. Notice that that's part of the commit, and because the commit is SHA-1 signed, the text relating to a commit is signed. So we can't have somebody come in later and change the text on us because it would be an entirely different SHA-1 and we know then something got tampered with. So this, again, is the power of having a nice cryptographically strong number to manage all this with. A tag is just really a commit that has a special purpose in life. It's basically an object that has some sort of subject so we can keep track of it. It's given a name, a nice identifier, and an optional payload. When I say, if I'm Linus saying this is the release of the kernel 2.6.22, I can attach that to a commit, and everybody will know that that really was me saying that. Optional GPG signature as well to cover that. So tags aren't really too special. They're just giving a unique name instead of having the hex, the 40-character hex string to assign to a name. So these objects are all living in the repository. Git efficiently creates those objects as needed. So as we change data, update data, we're going to be adding things to the repo. And the objects are generally added, not destroyed. This means that we can have concurrent operations in our Git working tree that still work because we're basically just adding objects to it all the time. There is a way to go through and do garbage collection, but there's a warning message by that says your repo needs to be absolutely static. Nothing else can be working on it when we're doing the garbage collection. Objects are actually placed very efficiently immediately into their own file in the repo, but we can run cleanup processes on those. There's a tool called git-gc that will go through and pack them. A packed object is often stored as a difference from some other packed object. So there's a lot of calculations made to really make the repo be as small as possible. And so we go through from time to time repacking things just to make sure that the repo is consistent. And so, yeah, as I said, packs are often representing those objects then as deltas so that similar objects, say a large file with maybe 3 lines changed in the middle, can be represented very efficiently in the repo. So we don't have to have lots and lots of different full text files for different versions. Packs are also used as the way we transfer things between repositories. So when my Git client is talking to a Git server, they will exchange information about what needs to be sent. The server will then create a pack so that the transmission space is as most efficiently possibly used as it can be. Of course, commits are what we're doing. We're making work. We're changing things. It's the whole point of a change control management system is to manage that. So commits are the rule. So again, one or more commits form the head of all the object chains. So that's what we call these are the branches. A branch is basically a commit that's at the head of an object chain. And there's typically one called master, and that's really only by convention. There's nothing special about the name master. It just happens to be the one that gets created when you first initialize a database or initialize a Git repository. But you don't ever have to have that one. You can delete that one and make it something with your own name in it. But people just tend to leave the one called master because it's easy that way. And you can make others at will. I mean, like I could be, for example, trying to fix a particular problem. So I'll create a branch called fixing problem X. And I'll start going off in that direction, making commits on that are deviating now further and further from my original master. And at some point, I'm going to say, yes, that commit, that sequence of commits does what I want it to do. And then I will merge that back into master. And that becomes my new master at that point. But there's really nothing special about master. So everything that's in the repo that I'm going to be able to access comes through these special top-level commits. So I'm always drilling down from these top-level things. If you want to think of it as a giant tree, these would be the leaf nodes of the tree. This is the tail end of it, or the head end, depending on how you look at it. So with each one of these head commits, as I said before, you've got the tree represented as one SHA-1, and you've got the parent commits going back in time, going the other direction. So again, this commit gives us the entire history and the entire current state of what a particular commit, a particular working tree looks like. So you chase down the parent objects to get the earlier commits and their respective trees. So we can always get to that. When you first create a Git repo, you're creating a commit on the very first hit that has no parent commit, obviously, because you're not deltaing it off of anything else. So a brand new repo will have a commit that doesn't have a parent. Sorry about that, it's orphan. Okay, so we then need to have a place to do our changes. We have to have a working directory, a working tree. What's one of the nice features about Git, though, is that there is a .git directory at the top level of your working tree and nothing else. There's no additional pollution of every directory all the way down, as some of you that are familiar with CVS and SVN and probably just about every other change control system know. So there's no pollution of deeper directories. It's grep-r friendly. It's very nice. All you have is this one .git up at the very top directory. And that Git directory contains all the meta information that's needed. All this is where all your repository objects are and things like that. There's a plain text file called config. It's .ini style that you go in and edit, and that controls the behavior of all the other tools, all the other changes and things. There are tools actually to edit it from the command line too. If you really don't feel comfortable running a text editor, well, of course, then why would you be building stuff? But if you're not comfortable with the text editor, there's also a tool that can allow you to add things and check values and things like that in this file. There's the objects repository. It's done like a 2 or 3 level directory thing. I never need to look in there. The tool just manages it for itself, so it just goes in there. And then the heads, which are the things that you can make commits onto, are in ref/head/whatever, and they're, again, plain text files. I think Linus has an aversion to anything that's like binaries in here, so almost everything is plain text files when it can be. And those heads, for the most part, are just a 41-byte string, the 40-character hex string with a new line on the end. So they're very, very lightweight. A branch is nothing more than a 41-character string, which means branches are incredibly lightweight. Their new file gets created in here. In fact, you could just type in an arbitrary hex string that, as long as it maps into your object tree somewhere, it would call that a head without having to do any other changes in your database. Tags are similar, same sort of structure, but again, they're referenced by slightly different commands. There's commands that know only about tags versus references. There are logs being maintained. Once they're enabled, you can then look at the history of a particular tag or the history of a particular commit. This lets you do things like, I want this branch at 4 p.m. yesterday, because the logs would know exactly what happened. Otherwise, we have to do everything simply by referring to the 17th parent, which isn't very exciting. So there are logs being maintained that have date stamp relationships, which are really nice. And most of the time on your repos, you're also going to be tracking other people's work. And so under the refs remotes area, we create what's called tracking branches. These tracking branches are just like the ones under refs heads and refs tags. They're going to contain the 41-character SHA-1 representation. But they're pointing at stuff that you got from somewhere else. So it's not stuff that you're making commits on. It's stuff that you're tracking that other people are doing. So commands can use all these interchangeably, but generally the remotes are things you're going to be tracking on and not committing on. You're committing on your local branches that are in refs heads. There's also the index, which is sort of interesting. It's probably the least understood part of Git. I can't even say I've got my head fully around it, but it is essential to know about it for certain operations, and I'll get to that in a second. And then finally, there's this one file in there called head, and all it is it contains a pointer to one of the things in refs heads. It's the current branch, whatever current branch means. It means the things that you're going to be making commits on once you say commit. It goes through the head, which then points at one of the branches and then makes the commit on that branch by adding a new commit to that one, making that the parent. So the interface between the working tree and the object repo goes through this intermediate thing called the index. And Linus has said a number of times that he could just as easily call it the cache, but then it would still be just equally mysterious. So he calls it the index in most of the documentation, so I'll use that terminology here. But he says it's more really just a cache. It's to speed some things up. We really wouldn't ever need it, but it's in there and so on. It's really a directory of blobs, a directory of file contents. It's really where the next commit is getting staged. So when you actually say commit, what you're doing is turning the index into the next commit. Now, that means that as you're editing files, and you're going back and forth, editing this file, editing that file, and so on, Git isn't tracking that. It just simply says, oh, you've got files that you've changed now. It isn't until you add it to the index that Git says, oh, okay, now when I commit, this new contents of this file will be part of the next commit. And what this lets you do is actually have sort of a dirty working directory where you have some files in there that you've updated. Maybe you've enabled a debug flag or something like that, but you don't really want to commit as part of your commit. You simply change it, and Git will tell you, by the way, you've changed this file that I'm normally tracking, but you haven't told me to take this version and make that the new version. So it lets you know that, but you can tell it, no, I want you to leave that file dirty. I don't want that to be part of this next commit. And so the index lets us do that staging for that. So we don't add it to the index till we really want to make that part of the next commit. So of course, committing it then is going to take that index, turn it into a real commit object, and then we're fine. So the differences between head, which is the current commit that we have, and the index will be anything that I've changed and told it it wants to be part of the next commit, but not yet committed. The difference between the index and my working directory will be things I've changed, but I haven't yet told Git, yeah, go ahead and take that version as the next commit. And also anything that's untracked. So I can tell Git, this is nothing you're paying attention to, and that, of course, would be a difference between the index and the working dir as well. And the index is also used particularly when you're doing a merge. When a merge fails, the index doesn't have anything in it that is conflicting. So it's up to you to then go back and say, edit the files that need to be changed, then add those to the index, then finally make the final merge commit when that happens. A merge that is successful by itself, of course, will go ahead and just produce the new commit and update the index to reflect that. One of the things that's interesting about Git, well, there's lots of interesting things about Git, but here's one of them, is that Git doesn't record any explicit renaming. Now, this is an interesting debate that comes up about every 2 or 3 months on the Git mailing list. It's like, why isn't there some sort of track that I really did rename this to that? And going back through the archives, you'll see over and over again Linus and the key developer saying exactly the same thing, which is that basically exact renaming can already be determined by the SHA-1 comparisons. If I take this file and move it over here, it has the same contents. So therefore, Git can notice that that's been a rename when it's doing merging and when it's doing logs. If you ask it to, it can figure out that those two are related. But what's even better about that is that if you copy a file to 2 different places, then all 3 of those will have the same SHA-1. And if you made a change in one of them during a merge, you probably wanted to make the change in the other ones as well. So by not having explicit copies and explicit renames recorded, we actually get to do better tracking, better merging, easier merging than if we recorded those explicitly. So the thing is, because the computer can find these far easier than you can, you don't have to worry about you leaving one of those out, it'll just find it for you. And the problem is, if you make it explicit, it's going to be wrong sometimes. You get A renamed to B and A renamed to C conflicts, and so on. Those never show up in Git, at least not in the main sort of way. Because when you're wrong, of course, it's going to break merges. Bad idea. Don't want to be breaking the merges. And even being right will break some merges. So the essence is that what Git is doing is tracking the snapshots of the result of whatever you're doing. I mean, you could take all the contents of the file away, type it all back in from scratch, and as long as it has the same SHA-1, it goes, yeah, same file. It's not tracking the actual container, it's tracking the contents. And that makes Git a lot more flexible than some other systems that I've used in the past. Git, of course, is good at transferring stuff between repositories. All the basic protocols there, you can just simply rsync a repository from one place to another, and in the new location it works just fine. HTTP and so on, the Git protocol, of course, being really efficient for transferring stuff from server to a client. SSH protocol, Git over SSH, I should say. And of course, local files. Git also has the ability to speak well, play well with others. There's full import and export with CVS. For example, I use Git to track a number of projects that are published as a CVS archive. And what's great is that I can then, at 30,000 feet, up in a plane, not just by myself, that would be a little hard, but up in a plane, I could be sitting there offline looking at the entire history of this archive that's being maintained in CVS, this project being maintained in CVS. And I can even make commits and make changes and test things and so on, whatever I can do in the, in my airplane chair there, probably not everything, but a lot of things there. And then when I get back on the ground, I can take that and push it back as a CVS commit. So the people on the main part of the project have no idea I'm using Git, have no idea I'm tracking the project with Git. And this is tools that are in the core to handle the import and export of that. Also SVN as well, import, export with SVN. There's import from Arch in the core. And as I said, I'm using CVS and SVN import to be able to have access to all of the data of a number of projects I'm tracking available to me when I'm offline, 30,000 feet or wherever I might be, middle of the backwoods somewhere and so on. There are a bunch of other third-party solutions out there. They're not part of the Git core. I know that there's a very, very interesting project to make a really fast Perforce importer for Git. I know that's important to a lot of you guys here, so I wanted to bring that up. So yes, there's people working on that, solutions going in and out like that. This is also sort of interesting. Suppose you're in charge of the repo and you say, okay, great, our project is migrating to Git now. We're going to get rid of CVS. We're going to use Git from now on. But then you've got a couple people there on their ancient laptops or desktop machines, and they don't want to learn Git. All they want to do is keep using their old GUI CVS tool that they've been using for a long time. There's actually a CVS server in the Git distribution that sits on top of a Git repo and lets them make CVS commits and checkouts, just like they're using CVS still. So that's a great way to go back the other direction for people that are legacy, people that just don't want to relearn anything, don't want to learn the 5 commands that they'll need with Git. And so it's great because that means the repository can act for legacy clients or humans. I like that. Legacy humans, I guess, probably fits pretty well for that. I must use CVS. It's what I've been using for 22 years. I can't learn something new. Right. So for people like that, we take care of that for them. You can get Git from the Git repository. Of course, then you have a chicken and egg problem. If you don't have Git yet, how do you use the Git protocol to get Git? How many times can I say Git in a sentence there? So you can get it using just a standard tar.gz that you can unbundle and compile, and then you will have Git, so you can download the latest version of that. There are packages available for all the modern standard archives and so on. And once you've bootstrapped Git, you can actually git clone the Git developer archive. That's hosted on kernel.org and also the Git repository at repo.org.cz, something like that. I get that. I track it every day, actually. I say rebuild once a week or so. There's a fairly stable branch of that I've never had problems with, and there was only one time in the entire 2-year development when something unstable actually was slightly dangerous. So it's really a fairly reasonable thing to keep tracking, and it's great because you can give feedback then to new features and things like that back to the development team. There's also a maintenance branch that's like even lagging that a bit, where they have like major announced releases on that one. But the stable branch is not bad. It's like it changes every day, but again, there's only been one time in 2 years when it was actually dangerous, and immediately the flag was raised on the mailing list to say, whoa, wait, this will break something, so don't download that yet. Okay, so it's not too bad. The maintenance release is very stable, right? And I install mine in opt-get, that way I can get out of the way. And I just add opt-get bin to my path. There's about 40 commands that gets installed there, so you want to add that to your path to be able to access all that stuff. Speaking of the commands, all the commands in Git start with git dash. So that's pretty easy to kind of identify what's a Git command and what's something else. And, but in order to make it possible, so you only have to add one thing to your path. There's just a git command by itself, and if you give it arguments, it will map itself into the other command. Git mumble foo will actually be the same as git dash mumble dash foo. You can type in either one and it works exactly the same. This makes it a little confusing when you're reading tutorials and online information about Git, because some people prefer the git dash convention, other people prefer the git space convention, but they're really talking about the same set of tools. It's just that different people use different conventions. Might as well. So the nice thing about this single Git tool is that you can put just that entry and say use a local bin, and everybody has access to Git through the single entry point, rather than having to have an entire directory added to everybody's path that wants to use it. And it also works for all the internal calls as well. The man pages, of course, are still going to be under git-mumble-foo, so you'll have to know the convention either way. You'll have to know that the real full command is named with git dash rather than git space. But of course, you can always use git help mumble-foo, so it still works. So pretty easy there. Of course, the internet is just a series of tubes, we know that. And that's carried forward into the Git metaphors. The low-level Git operations, Linus decided to call plumbing. And of course, what does that make the higher-level operations, or porcelain? So you'll see the terms porcelain and plumbing a lot in the Git documentation. The key difference between porcelain and plumbing is that generally you won't be invoking the plumbing directly at the command line. They're basically tools that are there for other tools to use. Some of the porcelain actually uses some of the existing plumbing, shells out to call various subtasks and so on. More and more of the porcelain, though, is being rewritten as monolithic processes using the library that's slowly being developed for Git, so that they don't actually call the plumbing anymore. But the plumbing's still there and is reasonably designed so that you can write your own custom tools using the plumbing that's available as shell calls back and forth, and be reasonably assured that, say, you know, spaces and strings don't get messed up and stuff. Almost everything has like 0 padded values as an option and so on. So really good for writing layered stuff on the plumbing that's available. So the distro includes both Git plumbing and Git porcelain. Some really nice stuff in there. I don't know what Git GUI is doing in that slide. Okay, so I'm going to be showing the Git porcelain in the rest of the talk, unless otherwise noted. So we're basically staying at the high level. There are some other porcelains that are out there. There's stacked Git, which lets you manage a set of changes and rearrange them as necessary, reapply them to different branches. It's nothing you couldn't do by just typing the actual commands, but it lets you manage it in a little bit more controlled way if you're used to the stacked things that come from, I guess, BitKeeper and a few other places. There's Gilt. I haven't used that, so I don't know what it is. You notice the play on the letters GIT. They love adding things to GIT to make other things out of there. There's TIG, which is a curses-based viewer, so if you really like to have stuff in old-style curses windows, that's fine there. There's QGit, and I haven't played with that one either. I'm not much for GUIs. I'm using my Mac here, and it doesn't like firing up X11 very often, so I basically am just using the command line stuff for most of what I'm doing. There are also some other porcelains out there. There's some plugins for GNU Emacs, so you can do VC mode correctly and so on. So that's all managed by Git, and that's mostly how I'm interfacing with Git these days. So how do we create a repo? Might as well get to that. Don't have much time left, so I'll keep moving here. Use git init. It's going to create a .git in the current directory. You probably want to edit at every level. You can edit a file called gitignore. Of course, you can just have one at the very top level if you want and have it refer to all the subdirectories down there, or you can keep it closer to where it's actually being used. Git add command sets up the files and adds them to the index. So staging it ready for a commit, and then git commit is going to generate that initial commit. So that's what's actually going to take a repo or a working directory that I haven't been tracking and turn it into now a git tracked directory. And that's all there was to it. That's going to create a branch called master. The current branch, the head, is going to point at master, and I'm ready to start making changes or publish it or whatever I have to do from there. Mostly, though, rather than starting your own repo, what you're going to be doing, if you're typically working in larger groups, is you're going to be cloning somebody else's Git repository. We'll use a remote spec there. It's going to create a repo from an existing repo. Generally, it's going to create a subdirectory below the current directory that you're in. And again, your work files are going to be in there, and Git's going to be in there. And all the branches that are in that remote repo, by default, are also become tracking branches locally. What this means is that later on, I can issue git fetch, and it will try to bring my repo up to date in parallel all of the remote branches that I'm originally tracking. Now, I can add and delete those remote branches as I need, but basically, I'm pulling down and fetching the remote repo now, tracking it automatically. And the remote head branch is going to be checked out as your initial master branch as well. So generally, what you're going to be generating, if you're using a Git archive or Git repos, you're going to generate more commits. These are always going to be on a branch. So a branch is just a commit that has a name. So master or my experimental work or whatever. It's just going to be a name of where I'm adding new commits with those. So when you make a commit, the former branch head will become the parent of the new commit. So that's how we create essentially a linear tree from there. Branch head moves to become the new commit. And so you're really creating, to use big fancy words, directed acyclic graphs rooted in the branch heads. So what you're doing is basically adding commits on top of existing commits, and that gives everybody the history there. So merge, as I said before, is just a commit that has multiple parents. So your typical workflow, your day-by-day stuff, edit, 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 right? Git add whatever you've changed. This is going to add the files to the index. Remember, the index is the staging area for the next commit. Git add will add all the interesting files except the ones you're ignoring. And then you say git status. I do that just before I do a commit to make sure I'm not committing something that's weird or too many file stuff. It gives you a complete listing of all the things that are being committed, all the things that aren't being tracked that you haven't told it about, all the things that are changed but you haven't done git add on in case there's some of those like that. That's pretty good. There's the difference there. When you're ready to commit, git commit. You can pops you into a text editor, so you type in your normal commit message at that point. You can also immediately pass a message if you want, similar to most other tools. The first line of the commit message is used for some kinds of logs. So you want to make sure that that's uniquely identified. Just the brief summary is the first line, and then the rest of the text is whatever you want, the details that you want. Current branch, therefore, is moved forward, and then you're back to more editing. So that's your typical workflow. Just go through this sequence here, like most source code managers. Now, what branch, though? As I said earlier, Git encourages branches. A branch is just 40 text bytes in a new line. So very, very cheap to do. So a typical workflow would also involve, when you're starting on a new topic, is to think of something to do, and you create a brand new branch. Git checkout-b, topic name, that's whatever you want to pick, saying, my experimental work on foo, right? And you're saying I'm basing that on master, which is what that last parameter is there. Work, commit to topic name. So every commit now is going on topic name now instead of onto master. And when your work is done, we would want to merge that back into the main line. So git checkout master, git merge topic name is going to take all those commits that we made in that direction and place them now on top of master and move master forward. So that's the typical workflow. And then I delete the branch because I no longer need it. Throw it away. It doesn't need to be there anymore. The -d is only permitted when it's a subset of head. Like, let's say you wanted to skip that middle merge step because whatever you tried didn't work. You could just type git branch -D topic name, and it says, okay, you don't have that branch anymore. It throws away all those commits, and there's no record of it after that. It's completely gone. Not even to you. Once you say git GC and get rid of that, it's gone. It never existed. My mistakes permanently erased. I love that. All right. Each individual commit is going to be shown. You can also take this entire branch with your 17 commits and say, no, that really is just one thing. I only want to show the one big commit that way. I would do a git merge -squash -no commit on this topic branch, and then git commit to actually make it one commit. So it's possible to bring them all in, so it's not like 17 separate commits, just one big fat commit. The nice thing about that git merge is it takes all the individual texts of all the commit messages and makes one big text file out of it, so you can pick and choose from that what you want to actually show in your final commit message. Very nice for that stuff. So, of course, you can have multiple topics active. I could be working on topic 1, trying to figure out how to make things work, commit, right? And then I go, wait, I also want to be working on this. I'm not done with topic 1 yet, but I also want to be working now on something else. Boss comes along, says, this is broken, fix it right now. So I will check out another thing off of master called topic 2, commit. Then I may want to work back on topic 1 for a while because the boss isn't looking for a second. I want to get back to looking at that other thing, commit, and so on. So now I've got master and 2 deviated directions off of that. So I've got a directed acyclic graph that's pointing me out towards topic 1, another one that's pointing me out towards topic 2. Okay, so now I have to decide how I want to bring them together. I can either merge them, which means if I look at a graph of it, it'll be 2 deviated lines that eventually come back together in a giant loop. Or I can also rebase, which says I'm going to take either topic 1 or topic 2 and make it appear as if it was attached to the head of the other one. In other words, make it a linear history down both. Each one, of course, has its pros and cons, so let's talk about those separately. The merge, as we saw before, we check out master, we pull in topic 1, we delete topic 1's branch, and this should be what they call a fast-forward merge. What that just means is that there's really no work to do. I just take these 8 more commits and I put them at the top of head and it just goes forward. Nothing changed there. But now's where the work's going to happen. Git merge topic 2, because there are changes in topic 2 at this point that are not in my current master. So now we have to figure out how to make it fix. So I could have made text changes in 2 different ways. There could be overlapping. That could be an issue. I could have renamed files 2 different ways and so on. So git merge topic 2 will either say, yep, done, or it'll say, nope, it's broken still. You have to go in and fix it. Tells you what's broken. Git status will show that as well. You need to resolve, then commit it. Then you add anything you fixed, or git add dot will also do it. And then git commit. And then there's where you describe how you had to actually deal with the merge. You can also abort. Just say git reset. It's going to bring you back to the state before the merge. So that at no point have I lost any state, lost any information. I can almost always undo everything that I start with. Rebase is different. It's going to rewrite the commits. The problem is, if you recall, though, that the SHA-1 of a commit also contains cryptographic information that defines its parent commits. So if I start moving around the parents of various commits, the SHA-1s are also going to change too. It really becomes a totally different commit. So I wouldn't do this if I've published it in some repo, because somebody already knows this particular state of my world as this particular number. I wouldn't rebase it then, because it would change the number even though it's at the same state. So don't do this if you've published anything. But for local repos, it's actually the best way to go. I rebase master on top of topic 2, and so all the changes in topic 2, but not in the master, are going to get rewritten as changes to the new master. Oh, this is rewriting topic 2, sorry. May result in merge conflicts, because now we're taking each one of these changes in topic 2 and applying it as if they were on top of the new master instead of the old master. And so some of them may conflict because changes were made in 2 different ways. So at that point, you'll get notified. You then say, go ahead, continue from here, or abort this entirely, or just skip this particular change. We'll just leave this out and we'll pick it up some other way. And when it's rebased, then obviously the merge is going to be a fast forward. And rebase has this wonderful interactive command that's really cool. You say get rebase-i and the same parameters you would have given otherwise, and it pops you into a text editor that says, take this commit, this commit, this commit, and ignore this one. Squash these 2 together. You can edit the text file to do a lot of different things. You can even reorder the commits. You can completely skip them out. You can comment them out. So it's really sort of a nice interactive way to do your rebasing. Okay, and so the merge will be a fast forward. Check out master merge topic 2. So that's the 2 basic ways that you're going to be merging your work with your own work in another topic, or merging it with other people bringing stuff in when you've brought stuff in from other repos. We want to be able to look and see what's happened. There's a nice log, prints out the changes. -p prints it out as a patch, so you can actually see it as, you know, these lines deleted, these lines added. --stat gives us a diff stat, which is really a nice summary. You know, this many lines got changed, this many lines got changed, and so on. Very nice that way. We can also ask for just the logs that affect certain files and directories, which really is nice when I want to see when somebody's changed just the documentation of a project. I can do a git log on the documentation directory, and it will track that down. There's also diff, where we give it 2 different file positions, 2 different trees, I mean, and it will tell me what the differences are. Git diff by itself is checking the difference between the index and the working tree. Git commit -a, make this empty, obviously. Git diff head is going to be the difference between what I'm about to stage and the head. So that's handy when I want to see what I'm committing again as well. And then cached is the 3rd direction between head and index. Okay, just running out of time here, so I want to get a few more slides in here before I start taking questions. Most of the commands take an arg that they call tree-ish, and there's many different ways to do that. We can either give it a full SHA-1, we could give it any unique abbreviation of a SHA-1, and because the first 8 or 9 hex characters are often enough to completely identify it, most of the time you'll just see people using short versions of that. Like they'll see a SHA-1 on there that's really long, they'll just pick the first 8 or 9 characters and type that in instead. And it'll still work, because as long as it's unique, it's going to be available. You can also type head for any of those commands that we just saw, a branch name, a tag name, some remote branch name, any of those followed by up arrow n to get the nth parent, or tilde n, which is going to be how many parents back. We can also pick a particular file or object out of a tree, which is interesting. And for example, we can say, give me the differences between the previous commit and the current commit. That's kind of nice. Find these things. Give me the 3 back to the current commit and so on, and what damage the last 3 edits did. Now, for graphical views, at the very beginning of the slide, you may have saw this nice tree of all the changes that have been made. And that's actually was a live dump of a tool called git-k, git-tk, I don't know how you pronounce that. It's weird. You read things online, you don't know how to pronounce them when you're actually in public. It's git-k, whatever. That. You say that, followed by my topic, origin, and it will draw a nice TK widget display of all the history. And it shows the changes back to whatever common ancestor those 2 had. And it also is live. You can go in and look at any one commit, and it will show you all the differences for that commit and so on. There's a lot of search tools built into that. This is really sort of your graphic view of all your history. It's very nice to use. -- all takes all your current heads and does the same thing. You can also say from one to the other, just the changes of two that aren't in from and so on. Keep going here, go, go, go. There's also qgit, which is similar to git-k. Again, I haven't used qgit, but that's there. When I do a clone, I'm creating these tracking branches. They're typically named origin/master and origin/foo for the foo branch and so on. So to share your work, you first want to bring it up to date. You would use git fetch. That's going to go to the remote repo, pull down everything that's changed, and update my local repo with that. And then you would rebase your changes on the upstream. And the reason you're going to rebase your changes is because it looks weird if all the projects have all these bushy branches sticking out to the side. So most commonly what people are doing is they'll take your current master, whatever your branch you want to publish, they'll rebase it on the remote's master, which means all of my changes are now sitting on top of the changes that I've just pulled down, and it would create a linear thing once I pushed it, and that's going to be really handy. Then I would push it upstream. If I have write access to the remote repository, then a git push will take care of that. If I don't have write access to the remote repository, like I'm just somebody who cloned it out of the blue and now have something I want to contribute, I would send it in as patches, git format patch, and then I would email those patches that are now left in the current directory. So a little bit of maintenance tools. Git GC is the garbage collector, goes through and takes all the unreferenced objects and gets rid of those, validates the object repository, repacks it into larger packs. Almost always when you get GC, you end up with one big file that has the entire repository in it, very, very conveniently packed up for it. Prune gets rid of the unreferenced objects. That's a dangerous operation. You can't do it while you're doing other things, and don't look when somebody else is looking. There's always ways to unwind your changes. You make a mistake and you say, no, I want to start over. There's git reset with various options. We're not going to go into the details here, but git reset basically forces the working directory and forces the index to look a certain way and just eliminate some of your changes. And don't do that unless you've published because you'll lose things. Every directory, as I said before, can contain a git ignore. It has very flexible syntax for files you want to ignore. It's handled via the shell glob if and match. Leading slash means the current directory and so on. Now, the git ignore files are checked into the repository and tracked by default, unless you git ignore the git ignore file, but that's kind of cool. You also have in your .git directory something called info/exclude, which is just like a git ignore, but only applies to your repo. And this is handy because like on my editing of the files, I'm going to be creating tilde files that end with tilde on the end, because that's what Emacs creates for me. But I may not necessarily want to force that to be something ignored for you as well. So I'll put that in my info exclude file, and then when I publish my repo, I don't have all these littered git ignores that say ignore the ones with tilde on the end. For configuration, many commands have some sort of meta information that they have. Git config is editing the .git/config file. Again, if you're scared of editing a .ini file, you can use a command to do it instead. Yes, you can edit it manually if you prefer. Git config name is going to get the current value. You can list all the current values in there. It prints them out nicely. There's also a global configuration thing, a .config file in my home directory, which will apply to all of my Git projects, and I can stick interesting things in there as well. Okay, so you want to set user.email and user.name for your commits to make sure that they're good. There's a lot of other tools that come along with Git. You can export the entire tree as a tar. Git bisect is interesting. You mark one commit bad, one commit good. It figures out a commit somewhere in the middle that's got like an even number of changes to both directions, and then says, try this. And then you say, oh, that one's bad also. So then it bisects the bad and the good again and keeps giving you halfway down, halfway down, halfway down, because every time you do it, you either say, this one was bad or this one was good, and it keeps narrowing it down until it finds the actual change that broke things. Very, very handy. Linus created this because obviously that happens from time to time on the kernel, that somebody will do something wrong, and so he has to do that. Cherry pick specific commits from another tree, bring it into your tree. Git MV is just a wrapper around typing MV and add and delete, so it's a little bit easier to do that. Git push, as I said, writes back up to an upstream. Git revert adds a second commit that undoes a previous commit. If you've made something, and then you realize it's wrong, but you've already pushed it, you add a revert, which will add a second commit that says, no, no, that was broken, and so both commits end up in the stream. That's better than if you just undid it yourself. Git blame, who wrote this, so you try that on a file, shows you all the different things there. And just on the last slide with about 2 minutes to go for questions here, I'll just put the information up here. Git and Wikipedia, of course, good pointer at that. And I think there's this tool called Google. I don't know if you've heard of it, where you can search for things on Git, and that's probably the easiest way to find things. I'm feeling lucky today. The Git homepage is there, git.or.cz. There's a wiki there. It's got a lot of good information. The FAQ is in there, a lot of great things. Pointers to presentations that have been made, papers that have been published, websites that talk about it. There's also a great mailing list, real high signal-to-noise ratio. Find out who else is using Git and so on. There's a Git IRC channel on Freenode, so check that out. There's people there all the time. Junio and the other chief maintainers are on there 24/7, basically. And that is that. I've got 2.5 minutes for questions, looks like. So let's start with the questions over here. Okay, let's take the mic so it'll go on the audio. Thanks.
Okay, so I'd like to hear your thoughts about very large projects. Like, let's assume we have KDE. What would be your suggestion to how to handle a base API library, base library API change that affects lots of code in the repository? So as far as I understand, the whole KDE repository is too large to be easily handleable by in one single Git repository.
Yeah, what they're doing with the KDE is they're breaking it up into sub-projects, and there's sub-module support that's being added to Git to manage that. I don't know a lot about that because it's still pretty new and still just being added, so I don't have any advice on that. Like I said, I haven't personally done large projects, and that just sounds like a nightmare to start with, but I'm sure Git would handle it reasonably well, or at least no more poorly than anything else handles stuff like that. Okay, yeah.
So I'm just wondering if there's some kind of way to take a bunch of changes that you've done that you now recognize, looking back, oh, those are sort of all part of a group, part of some larger change, and sort of make that explicit. So
yeah,
like maybe
at any point you could use
granting.
git merge as squash on 2 commits and say, I want to take this commit and everything that's in between it, and I want to make that one big commit and then recommit that. Now the problem with doing that, of course, is that you're changing the SHA-1 of everything forward from there. So because the SHA-1 controls the entire history, as long as you haven't published that to anybody, that's fine, because you're just saying, no, now it really is this way. So git merged as squash would take care of that, yeah.
Hi. Suppose a developer on my open source project has inadvertently committed some code that legally they shouldn't have done. It's still encumbered, but by the time we discover this, it's too late. It's already been published. Is there any way that we can have this code, this particular commit, completely removed from the repository?
Yes, there's a command called git filter branch that was designed to do specifically that, because that did actually come up in one of the repos. Now, the problem is you can't, obviously if I've already cloned the repo to my laptop, it's here. You can't force me to no longer have this on my laptop. But you can make the public repo completely remove traces of a given file or given text lines in a file and so on. Basically, it runs the equivalent of a sed command on every file name if you wanted to, or every text file if you wanted to, and rewrite all the commits within a range with these rewrite rules. So it's really, really good at that, yeah.
Sorry, this isn't really a question, but I'd just like everyone here to know that some of us have written scripts that let you use Git on Google Code. So if you want to use Git today on what you're working on now, go/Git in your browser or join our mailing list. It's git@google.com.
Nice.
Thanks.
Nice, cool. All right, probably one last question maybe. Yeah.
Hi there. So in the open source world, typically a person who's running an open source project will vet patches on a patch-by-patch basis, whereas in an organization like this, where there's a strong authentication between the company and individual developers, it makes more sense to vet a developer rather than, and so have the machine act as a gatekeeper for patches, having permissions or something like that. In other words, part of the reason why companies tend to use a central repository is that instead of having a person to review every patch, you can instead have a policy. Has anybody established a Git repository with such an automated policy?
Yes. Yes, in fact, there's a open Git repository at repo.or.cz that uses SSH keys to control who can publish to a public repository. So in other words, I can say that there are these 5 people on this project, and only those 5 people have access to this repo that's now publicly being published. And there are commit hooks that would let you control that. That's actually how that's done, though, is that it looks at the username that's being used to push to the project, and if the username's not one of the ones on the authorized list, it doesn't let the commit to succeed. There are hooks at just about every level of adding a file, uploading to a repo, and so on. Normally they do nothing, but you can enable them, and there's some very nice ones that have been written that are part of the contributory stuff, so it's in there. All right, I'm out of time. Thank you very much for your attention. Thank you.